All right, taking a quick look at 1D projectiles. Some of this is review from last week, but we'll get started here anyways. So if we take a look here, basically anytime we throw or drop something and it's going to freely fall or fly through the air, we have a projectile. And if we are dropping it straight down or throwing it straight up or throwing it straight down, we have the instance of a one-dimensional projectile. We simplify things for ourselves by making sure that we have no air resistance. And the nice thing about this is it does make a lot of calculations nicer. Allows us to kind of wrap our minds around the basics of what's going on without having to concern ourselves with lots of extra messy calculations. All right, so we looked at this last week, so I'm going to go through it pretty quickly. Right, so if we imagine a object thrown straight upwards, 19.62 meters per second, we are really good and can just nail that velocity. Anyways, initially that's our speed. Right, so time of 0, that's our speed. 1 second later, because it's accelerating downwards at 9.81 meters per second, we have its speed has been cut in half. We've subtracted 9.81 from our speed. And so an extra second later, so 2 seconds in, it's at the very top. It's actually at rest instantaneously or momentarily. And then another second later, it's 9.81 meters per second moving downwards. Oops, slow down. And then another second later, it's back to the same height we started with, moving downwards at the exact same speed that we started moving upwards. So the speed is the same, it's just directionally it changes. And in fact, we've got some symmetry stuff going on here, where initially we're moving upwards, and then at the end, when we're at the same height, we're moving downwards at the same speed. 1 second in, we're moving upwards. A second on the other side of rest, we're moving downwards at the same speed. And that's kind of the gist here for one-dimensional projectiles. If we have an object that's thrown or dropped, its acceleration is going to be 9.81 meters per second squared downwards. And this is true all the way through, even at the top of the motion when it's at rest. At any given height, the speed going up is equal to the speed going down. It's just that the direction is different. If the object returns to its original height, then the time to go up is the same time to go back down. Which also means if we know the time an object has been in the air, we know that the time it takes to get to the top is going to be half of its time in flight, or time while it's in motion. All right. If we drop an object, its initial velocity is 0. If the projectile is on a different planet or far from the surface of the Earth, its acceleration will not be our 9.81 meters per second, which means sometimes that's going to be the question, is what is the acceleration? Or you'll be given that extra information. Otherwise, we are going to make the assumption that this, settle down, 9, there we go, acceleration, even if the question doesn't specify it. Also, the object is rolled up or down a slope or rolling down some stairs or something like that, it is not a projectile. And so its acceleration is not 9.81 meters per second squared downwards. All right. So moving on. This is the question we looked at last week, so you can pause it if you need to. Object is dropped on the moon, lands with this speed. What height was it dropped from? All right, so we're given the acceleration due to gravity on the moon. We know its final velocity. We need to know we know the initial velocity because it was dropped. We want to know the distance. Settle down. Here is our formula off the formula sheet that we're going to use. Solve the problem. Again, you can look through this if you need to. Just to double check, this is a decimal point here. Also, in case we're concerned, this answer here is negative. That's the way it works out. It's because the object has moved or had displacement of 61.3 meters downwards. In terms of the way the question is worded, of course, we could answer this that it was dropped from 61.3 meters, and that's perfectly valid as well. I'll be specific in the question as to how I'm going to need you to answer. All right, so another example here. Rock thrown upward with a speed of 32 meters per second. Find the time required for it to return to its release height. So a couple things we need to look at here. First of all, when it returns to its original height, it's going to be going the same speed, opposite direction. All right, so if you want to think of it this way, this is the hidden bit of information. Right, we know we're on Earth, so this is true. We don't know distance, but we don't need it. And in this case here, we have to think, okay, well, formula-wise, I have this formula that says A average equals delta V over delta T. Remembering that delta V is really, so acceleration, or at least average acceleration, is going to be Vf minus Vi over T. All right, which then now we need to know T, so multiply both sides by T, divide both sides by A. T is going to be equal to Vf minus Vi all divided by A. All right, so I plug my numbers into here, remembering that direction is important, so I should also have arrows on top of things that are vectors. In this case, my reference system is that positive is up, negative is down. My time then is equal to, final velocity is negative 32. Oh, that's an interesting negative. Negative 32.0 minus my initial velocity, so minus 32. All divided by my acceleration, which is 9.81. If I'm doing this by hand or not on a computer, I am going to use units here, and what we'll find out is that meters per second minus meters per second gives me meters per second on the top, divided by meters per second squared works out to seconds as my units, so I've done this right. One more thing that I missed is that this is downwards acceleration, so there we go. I work this out on my calculator, making sure either to use brackets if I'm doing everything at once, so that I'm doing all of the subtraction on the top first, and I'll end up with negative 64 divided by negative 9.81. And I end up with 6.523955148, and so on. Seconds, I have 3 significant digits, so it's going to be 6.5 something. It's 6.523, so we round down to 6.52, units or seconds. All right, and then moving on to our, come on. There we go, sorry. Our velocity time graph, something goofed up. The V really should be underneath this arrow and not sneaking over here, or the arrow should be on top of the V, either which way. Anyways, if I do a velocity time graph here, I'm going to start with a positive velocity, as we looked at in the last question, of 32 meters per second. And I'm going to, at some point, half of 6.52 seconds in, I'm going to have 0 velocity, and then 6.52 seconds in, I'm going to be at negative 32 meters per second. So essentially, I'm going to have a straight line connecting these 3 points, we're going to pretend that with my mouse I can draw a straight line. Not too bad. Anyways, it's a straight line because if we think what's the slope? Well, the slope is the acceleration. The acceleration is negative 9.81 meters per second, or meters per second squared, which means I have a nice straight line slope. My velocity starts positive, it is gradually, essentially slowing down, and eventually comes to a rest instantaneously at the top of its trajectory and continues to speed up as we move downwards. All right, oh, settle down, that was not intentional. All right, so that's my velocity time graph. All right, moving on. Rock is thrown upwards to its original height in 8.4 seconds. Sorry, and it returns to its original height in 8.4 seconds. So if we think about this, motion is going to look something like this. So whatever height we threw it from, it returns to that in, ooh, that's a terrible arrow, a time of 8.4 seconds. So I have time, which is 8.4 seconds. And here we've got something important. We don't know our initial speed. We do know acceleration. And it looks like we don't have enough information here. I don't know a distance. I don't know an initial velocity. I don't know a final velocity, but wait. I do know a final velocity if I decide instead of looking at the whole time it's in flight that I look at half the time. Because I know that to go from here to here, this is halfway in the middle here. And halfway in the middle, I've got VF equals 0. And so my time that I'm actually going to use is going to be 8.4 divided by 2, because I want to have half of that. So that's going to be 4.2 seconds. And I want to know maximum height. I actually have a formula that I don't even need to rearrange. All right, so D equals VF T minus 1/2 T squared. These are vector quantities. I mean, we're dealing only with up and down, but we are dealing with vectors, so we'll put our arrows in. Lovely. So plugging in numbers, I actually have to put one more piece of information that I know down here. VF is 0. Which actually makes this whole equation even that much simpler, because this whole first term is going to be 0 times time, which is going to just be 0. So my displacement, or maximum height, my distance, is going to equal, let's just, for the sake of completeness, 0 multiplied by 4.2 seconds minus 1/2 times negative 9.81. And again, I got a minus and I've got a negative in here, so my displacement is going to be positive, which makes sense because it's moving upwards. Meters per second squared times 4.2 seconds squared. And when I'm punching this into my calculator, I probably am going to need to put brackets around the 1/2 if I'm leaving it not as a decimal. And this squared needs to only be applied to the 4.2. So however we do our brackets, it only can affect the 4.2. Otherwise, we will get a much larger answer than we actually should have. So we work that out right now. And my displacement is going to be 0 minus 0.5 times negative 9.1 times, and then I'll do this in brackets, 4.2 squared, and it's just the 4.2 that's in the brackets there, and that's the only part that's getting squared. And so 0 minus negative 86.5242 works out to two significant digits here, so 86.5 becomes 87. Meters. And so if I had to have a full sentence, its maximum height is 87 meters. All right. Now, one more thing that I should just talk about with this here, and that is, eventually, there we go, very important point here. Time up is equal to time down, which means the time to reach the maximum height is half of the total time. All right, so this is one of the tricks that we might have to use. Another trick we could use is this bit here, that the speeds match. Right? And so when the height is the same, the speeds will match. For this particular one here, right, the trick, if you will, is that it was dropped, which means its initial velocity is 0, even though we're not told that. All right. The other thing to do when you're doing these questions, especially question 4 in the assignment, make sure you look at the formulas carefully. There is going to be a formula that helps you with all of these questions. It's not necessarily a matter of me trying to trick you. Just look carefully at the formula sheet. Otherwise, have fun. Assignment is, I'll write it here, page, essentially it's 38 to 40.